Okay, so uh, that's the classical harmonic oscillator, and we can derive a potential energy for the harmonic oscillator. If we realize that the force for conservative forces, the force is equal to the spatial derivative negative the spatial derivative of the potential, and so if we integrate the force over position x, then we get the general formula of the potential is equal to 1/2 kx squared plus a constant. We can set the constant equal to 0 at x equals 0, and so we're basically the final form of the potential is 1/2 kx squared. Remember, we're free to set the zero potential energy anywhere we like, so we set it 0 at x equals 0. Okay, so the form of the potential is indicated here. This harmonic potential, okay, so is that's described by this function 1/2 kx squared is shown. An example of that is shown right here for a particular value of k. Okay, I don't have any units, and so it's pretty generic. And again, as in the square wave potentials, we have a classically forbidden region, okay, shown here in gray, which is where a classical particle would not be allowed to go. If you put a classical particle into the potential, then it would not be allowed to go. And one of the things that we already know from looking at the potentials, the potential wells, is that if we have a bound state in this harmonic oscillator potential, which we know we will, we'll have oscillatory functions inside and exponentially decaying functions outside. Okay, we know now that in quantum mechanics that the wave function can penetrate into the classically forbidden region. Okay, that is where the energy is less than the potential energy. So that's in this region, or in the gray region. And so a particle with that's in a particular energy state, again, we'll have oscillatory solutions inside. I'm just going to draw a generic one, okay, and has exponential decaying solutions outside. Okay, this is not meant to be a particular solution. This is just generic. We know that it has to have this form, oscillatory form inside and a decaying form outside. And we know that we're going to get even and odd solutions. Even and odd, that is the symmetric and antisymmetric with respect to the center of the potential, as we go up. And we know that we're going to have quantized energies because qualitatively this is no different than a potential well. It's just that the shape of the well is particular. It's a harmonic potential. Now, the reason why we study the harmonic oscillator is sort of a canonical thing to study in physics and in quantum mechanics, and that's because this harmonic oscillator potential, 1/2, or something which goes as x squared, is pretty generic, and it actually can be used to approximate other more complicated potentials, at least locally. So an example of that is shown right here. What I've shown in green here is the potential energy curve for two atoms in a diatomic molecule as a function x of their separation. So x is the separation between the two diatomic molecules. So if we think of this as kind of the center of mass, x is the distance between them, and this potential energy is the fact that it's attractive at longer range. That means it's negative and has this negative slope. Means that that's basically what keeps the two atoms in the diatomic molecule together. But of course, if we know if they get too close, then they start repelling each other.